Hello there and welcome to the October 2020 paper 1. Here we're looking at question 7. So a sample of bacteria in a sealed container is being studied. The number of bacteria P in thousands is modelled by the differential equation 1 plus d dp by dt plus P equals t to the power of half 1 plus t, where t is the time in hours after the start of the study. Initially, there are exactly 5,000 bacteria in the container. Now, what I did first of all in this question, I got it wrong, is I forgot to read that P was in thousands already. So what this information here is telling you here is that when T equals 0, P equals 5. Don't accidentally write 5,000 there, because P is actually measured in thousands. So, let's get on to the question now. Determine, according to the model, the number of bacteria in the container 8 hours after the start of the study. So first of all, let's just rearrange this differential equation. We'll divide by 1 plus t, so it's plus 1 divided by 1 plus t, p equals t to the power half. So from this equation here, I've divided by the 1 plus t. So now I'm going to go to my integrating factor. So my integrating factor is equal to e to the integral of 1 over 1 plus t dt, which is equal to e to the ln 1 plus t, so therefore it's equal to 1 plus t. So therefore the answer is going to be 1 plus t p equals the integral of 1 plus t times t to the power of half dt. Okay, so it's 1 plus t p equals, let's now integrate this thing here, expand the brackets, you'll get t to the power of a half, integrate that, you're going to get 2/3 t to the power of 3 over 2. And on this one here, you're going to get t to the power of 3 over 2, integrate that, and you're going to get 2/5 into t to the power of 5 over 2. And then plus c. Now we need to work out what the plus c is equal to by substituting in this information here. So when t is equal to 0, p is equal to 5. So t equals 0, p equals 5. Let's plug that in. T equals 0, p equals 5. And we're going to get 1 plus 0 is 1 plus times by 5. So that'd be 5 equals 2/3 times 0, oh, so that just cancels out. Oh, so it's just plus 5, isn't it? So c is plus 5. So therefore, we can say that 1 plus t times p equals 2 over 3 t to the power of 3 over 2 plus 2/5 t to the power of 5 over 2 plus 5. So now what I'm going to do is determine by the model the number of bacteria in the container 8 hours. Is t measured in hours? Let's just check t is measured in hours. Good, so we'll just plug t equals 8 in. And we're going to get 9p equals 2/3 8 to the power of 3 over 2 plus 2/5 8 to the power of 5 over 2 plus 5. So therefore let's just leave that 9p on the right hand side to get started, and let's work out what the right hand side is equal to. So for each of the individual parts, the first part is going to be 32 over 3 root 2, plus the second part is going to be 256 over 3 root 2, and then it's going to be plus 5. So therefore, if we group all of this together, group the root 2's together and divide by 9, we get 928 over 135 root 2 plus 5. 5 plus 5 over 9. So that's approximately equal to 10.3 to the nearest 3 significant figures, which in terms of the context of this question is about 10,300 pieces of bacteria. Okay, so there we are, that's the answer to part A. Let's now move on to part B. Find, according to the model, the rate of change of the number of bacteria in the container 4 hours after the study. So let's first of all grab that function again. It's going to be 1 plus t, p equals 2/3 t to the power of 3 over 2 plus 2/5 t to the power of 5 over 2 plus 5. And we also have the differential equation, the initial one, which was dp by dt plus 1 over 1 plus t, p equals t to the power of a half. Now if I want to work out the rate of change after 4 hours, what I think I'll do is I'll use this expression here, but in this expression here I first need to work out what p is equal to. So I'm going to use this as the first formula that I'm going to plug t equals 5 into. So t equals 4. 1 plus 4 is going to give me 5, so it's 5p equals 2/3 t to the power, 4 to the power of 3 over 2 plus 2/5 4 to the power of 5 over 2 plus 5. So in this case here, when I eventually divide through by 5, my p value is going to be 347 over 75. And then what I'm going to do is I'm now going to plug this value here into this equation here. So we'll do this up here. So therefore it's going to be dp by dt, and in fact I'm going to move this 1 over tp onto the other side, so it's going to be 4 to the power of a half minus 1 over 5 lots of 347 over 75, which will give a final answer of dp by dt equals 1.075. That would be, so what would that be in terms of the context of the question? It would be 1,075 bacteria per hour. At t equals 4 hours. State a limitation of the model. Well, according to this model here, it seems as if the rate of increase is always going to be positive. If you work out, if you have a look at what, if t increases, then the square root of t is going to increase as well. Yes, this bit here will tend towards 0, but it's always going to be growing. So effectively, in this model here, the number of bacteria is just going to grow infinitely for all values of t, where it's unlikely to do that. It's eventually going to run out of resources, etc., etc. So a kind of a reason like that. So there we are, that's the answer for this question 7 here, worth 11 marks in total. And that's all we've got to go through for core paper 1. Maybe let's move on to core paper 2.